So what we're going to do with the rest of the time today is start on this method for solving these problems, for solving boundary layer problems that you probably haven't seen before. Maybe you've seen it if you've taken like a advanced fluids class, but it's called the integral method. And the idea is that we have these ODEs. Let me scroll down here. So we have these ODEs for that govern flow in the boundary layers, but they're really actually hard to solve exactly. Think about what we're trying to do when we're trying to solve something exactly. We're going through deciding what the form of the solution looks like. So say we're solving for velocity profile, right? You have to come up with a solution of the ODE for the velocity profile that's valid for that ODE. In an integral solution, we actually don't solve the full ODE exactly, but we start off by making some assumption about what we think the boundary layer velocity profile is going to look like. So think about what I'm saying there. I'm saying we're going to make a guess about what we think the velocity profile looks like. And we can start here by saying my velocity profile, u over u infinity, is a function of, let's say, some function of the position y over the delta m, which is the boundary layer thickness. So I have this right, the velocity curve looks like this, right? So I have velocity that looks something like this in my boundary layer. I'm coming up with an equation for this line, right? This is some function of y over delta m, right? Where this position here is delta m. So if I can come up with an assumed function for that, maybe it's a function of position x, maybe it's not, right? Maybe it's sort of normalized. I can then substitute that, my assumed solution back into the ODEs, do some kind of integral calculus, and you end up with a solution that gives you the boundary layer thickness. And then you can use that to do heat transfer calculations or viscous calculations. So we're ultimately trying to assume forms of these, go through, solve, apply certain conditions, which I'll show you how to do. And then we end up with ODEs that give us our boundary layer thickness, and we can use our approximate models for calculating then the quantities we care about. Okay, so let's go through this. I covered. Oh, one other thing on the side here. I wanted to note. So we're doing this. We're going through this process, assuming some function here that we're going to solve the ODEs. I've mentioned a couple times the exact solution for boundary layer thickness, and it involves this thing called a self-similar solution. I just wanted to make a point that the self-similar solution is actually really similar to what we're doing here. It's just that the self-similar solution says, I'm going to go through and come up with this function here in terms of y over delta m. So y over delta m is actually something that changes, right? It's let's say, so delta m is changing with position x, right? The boundary layer is growing. So y over delta m is sort of the normalized position within the boundary layer. The exact coordinates of that are actually changing as a function of position x. In the self-similar solution, what we're doing is we actually say this single variable eta corresponds to y over delta m. We have now a single variable instead of having x and y. You go through and solve the ODEs for that single variable, and that's the self-similar solution. We won't go through it. It's in the book if you want to look at it, which I think I mentioned before, but it's kind of a similar thing to what we're doing here. All right, so let's see. So how does this integral method work? Well, let's go through, again, we do this for both the momentum and the energy part. So let's start by looking at the momentum equation. Let's write out, I should have copied this from before, but let's just write out our momentum equation in the x direction. So it's rho times u du dx plus v times du dy equals minus dp infinity dx plus mu d squared u dy squared. Right, that's our x momentum equation. So what we're going to do in this is we're saying I'm going to actually take my function, whatever my function is that I'm assuming, and I'm going to plug it in, and I'm going to integrate this whole thing. So I'm going to integrate this whole equation here from y equals 0 to y equals delta m. as a function of position y. And so I'm integrating that whole equation. Now, how do I actually do that? Well, there's a whole proof in the book that, again, I'm not going to go through because it would take the whole lecture period. But what you end up with is, so we take this, do this integral, and then we end up with the following kind of somewhat messy equation that we'll go through in more detail. So we end up with, let's see, so it becomes dx of the integral from y equals 0 to delta m of the quantity u squared minus u times u infinity dy. Okay, so that's the first term. There are 4 terms altogether. Second term is the derivative du infinity dx times the integral from y equals 0 to delta m of u minus u infinity dy. Okay, then the third term is, let's see, plus the velocity v at y equals 0 times u infinity minus u at y equals 0. And then the fourth term is equals to, on the right-hand side, 1 over rho times tau y at delta m minus tau s. Okay. Hopefully that's okay. So there's quite a bit of stuff involved in that arrow, which again I won't show, but we end up with this equation, and it kind of looks funny, right? There's stuff there that we shouldn't expect to see. In our solution, what we've done before is we've done things like, okay, at the surface, there's no slip. Well, that's our assumption. It's not always true. There could be conditions where there's actually a velocity at the surface. Like what happens if you had diffusion of mass across the surface while there's flow in the boundary layer? So you have some y component of mass flow going while at the same time you have flow. What happens if, let's see, what else? I mean, I could just label these terms a little bit so you can kind of see where each of these become useful. So this is our momentum change. So momentum change. This is our pressure force. Pressure force. This is here. Momentum injected at surface. And this over here is our shear force. All right, so we've written these in a general way so that, let's say I have momentum coming in at the surface. Let's say I've got any other number of conditions that actually make the original assumptions too difficult to solve. We can still solve it with this method because remember, we're assuming a velocity profile. Like we're saying my velocity profile looks like this. I don't have to have the exact analytical solution. I can assume it and then sort of force fit it into this equation. So we have, this is our kind of general equation that we have. And then what we need to do is go through and decide for a given example, which of these terms are important, which of them are dependent on position, and then solve for the boundary layer thickness. So let's see, same thing for energy. Let me just do a little divider here. So for energy, our energy equation was, if you remember, it's rho c u dt dx plus v dt dy is equal to k times d squared t dy squared plus mu du dy squared. All right, again, we're going to take this equation, cheat a little bit and move this over. Okay, so what we're going to do is take this equation and integrate this equation from y equals 0 to delta m, or sorry, delta t now. Delta t, right? This is the thermal boundary layer. We're doing that entire thing over position y. right? And then again, the same thing, we have this messy proof that gets us to the following equation. So I'll write it out. It's d dx of integral from 0 to delta t of, let's see, u t minus t infinity dy. That's equal to, on the right-hand side, we have v y equals 0, ts minus t infinity, plus 1 over rho c times q dot double prime s minus q dot double prime y equals delta t, plus mu over rho c integral 0 to delta t of this du dy squared dy. Okay. So now again, we have this equation where we can make, we can relax some of the assumptions that we had. Like, let's look at, let's q double prime s minus q double prime y equals delta t. What's that term allowing us to do? It's saying I could specify a flux at the surface, right? Q double prime s. I could also specify a heat flux at the boundary layer edge. So let's say you have a flow where there's actually significant conduction into the fluid at the boundary layer that's still occurring. You can force that to be true with this equation. So you can do quite a lot with this to make it fit really any problem that you might have. Okay. Let's write some of these out. So this is this first one here. I didn't leave much room. This is enthalpy change. Let's see. This second one here is energy due to fluid motion. Okay, third one is which is the one we gave, that's conduction. And the last one here would be viscous dissipation.